Okay, welcome everybody. We are going to finish all the material today. We almost finished last week. We were in section 8.2, and that is the last section that we'll be covering. And I said most of the stuff, but I think there's just a few more things we need to touch on, and that'll be everything that we need to know for the final. Final exam I'm planning on having on May 21st. That's Thursday of not this week, but next week. And you'll be able to start at any time between 10 a.m. and 8 p.m. It'll be just like exam 3. So you'll have about 3 hours to do it. I may think about that. I'll let you know what the final timing for that exam will be. But you'll be able to start at any time between 10 a.m. and 8 p.m. on that day, Thursday, May 21st. If there are issues with that day, email me and let me know, okay? And it will cover everything. It will cover everything from chapter 1 to chapter 8. Now, we skipped some stuff on the way, so it's, I think we skipped chapters 6 and 7. So, but everything that we covered is going to be on the exam. And you can review for that exam by going to My Open Math and looking in the exam review sections that I posted on the top of our course page, which has the copies of the homework assignments that you can go through and practice. And I think that's the best way to practice for the exam, is just go through those homeworks, because I think, as you noticed on the last couple exams, that's how I created them. I just pulled problems very similar to the homeworks, maybe not identical. Some of them were almost identical, but they're very, very similar. So that's the best way to study for the exam, is by reviewing those problems. And in those problems, you can see the solutions. So that's a good way to practice. So let me show you that, and I also want to show you a schedule of all the topics that we covered, just so that you can get an idea. And then we'll talk about these problems that people are asking about. People are asking about problems from sections 8.1 and 8.2. So we'll take a look at those. So I'm going to share my screen here. Oh, and then we'll review some of the final material. This Thursday, we'll just have the day for review. Okay, so I'll hold class, but I'll just be here to answer questions. I won't be covering anything new. So if you don't have questions, we'll call class short. But if you do have questions, I'll be happy to go over anything from chapter 1 through chapter 8 that we covered. Okay, so I'm going to share my screen here. Here's our course page. Notice at the top, we've got all the review sections. So if you want to go and practice problems from these sections, just click on the corresponding section area. And the old exams are here too. So if you want to go back in and practice exam 2, you can do that. And it'll give you problems from exam 2, and it'll even show you the answers. Exam 3 has been graded, and it's in the grade book. And also in the grade book, I have dropped your lowest exam score. So your grade is up to date. The 2 labs that were completed, those were both graded. I dropped the lowest of those 2 lab scores just because I decided to do that. I wanted to have a lot more labs, but we didn't really get around to it. So only the higher of those 2 scores is counted, and only the 2 highest of your 3 exam scores are counted. The final exam score will not be dropped, okay? So no matter how you do on that, that will be included in your grade. I wish, let me try, while I'm talking about grades here, let me try something. I want to log in as a student and just point out, so we're all clear, how to check our grades. I need to log in with another browser so I don't lose my login on the other one. Okay, this should work. Let me share my Firefox browser here. So here's my fake student account. So if you go to the gradebook, you'll see this. You'll see all the assignments and how you've done on them. Okay, so you got your grades here. This fake student, I only completed the first couple, and the rest not so much. We have our labs in here. So you got the lab grades. If you see a D, so I guess I got 3 lab grades in here. I mistakenly said only 2 before. We got the 3 in here. If you see a little D by a score, that means that score has been dropped. All right, so it's not counted in the grade calculations. So you'll see the lowest exam score was dropped, and the lowest the lowest lab score and the lowest exam score were dropped here. And then at the bottom, you can see how your grade is computed. Don't look at this column, past due and available. It doesn't make sense to count assignments that are available but not yet due in your grade. Only the assignments that have been due should be counted, because those are the, you probably haven't started, you may not have started the other ones. So only look at this first column here, and you'll see that in this first column, you've got your homework grade, your lab grade, and your test average. That includes everything but the final, right? The final will come in as a 4th row here, and then altogether these give you a weighted total. So this is your weighted average. So because I haven't done many homeworks and stuff, I have a very low weighted average here for my fake student account. I was wondering if it showed you the weighting on here. I adjusted the weighting because we couldn't get around to doing the research project. So I distributed the percentages from that research project onto the exams and the homeworks and the labs. I'll try to post oh no, it's right here. It's right here. Homework is 20%, labs 10%, tests 35%. The final will be the remaining whatever percent there. You're a stat student, you can figure it out. So the final will be the remaining whatever percent. Okay, so that's how you can check your grades and stuff. And please look through exam 3 and look at the comments. I don't know if you click, well, I didn't take exam 3, so I can't do it, but you should have a little link here to click on your grade, and you should be able to look at comments. I think you'll actually even see them. Yeah, view feedback. Click this little view feedback link, and I may have written feedback on different problems. Okay, one common feedback that I did leave is no work upload found. So some of you, I didn't get any upload of work that you were supposed to show for the problem. I looked through my email, because some of you had emailed me instead, and if I didn't see it there and I didn't see it on My Open Math, I just wrote a little blurb here. If you are confident, 100% sure that you sent me the work and I left you this, then you should contact me ASAP, okay? Because I gave you no points for the work if I didn't get the work upload, all right? And that was a substantial part of the exam, was the work that you showed. So if you see this message and you feel like it's an error, let me know, okay? All right, so we were going to look at some problems here. Question 3 in section 8.1. Let's take a look. So we were talking about in chapter 8, scatter plots. And so this is a question. Let me zoom out just a little bit for this one. Okay. All right. Beer and blood alcohol content. So many people believe that gender, weight, drinking habits, and many other factors are much more important in predicting blood alcohol content, BAC, than simply considering the number of drinks a person consumed. Here we examine data from 16 student volunteers at Ohio State University who each drank randomly assigned number of cans of beer. These students were evenly divided between men and women, and they differed in weight and drinking habits. 30 minutes later, a police officer measured their blood alcohol content in grams of alcohol per deciliter of blood. The scatter plot and regression table summarizes the findings. So here we have the different amounts of beer drunk in cans and the BAC, the blood alcohol content on the y-axis. So each dot represents an individual person. And so corresponding to each person, they have a certain amount of beer drunk and a certain blood alcohol content. And we see it makes a scatter plot. It says to describe the relationship between the number of cans of beer and the VAC. Now, I don't want to answer this question because it is a homework problem, but we talked about, if you look at the last class's video, we talked about different kinds of relationships: positive, negative, linear, nonlinear. This distribution of points here, you can answer this question, whether it's positive, negative, strong, or weak. Write the equation of the regression line. Okay, this might be why you're asking about this. It looks like maybe this should be in the next section, 8.2. We didn't talk about writing down the equation of the regression line until section 8.2. Okay, so I should probably move this exercise. I can't move it now that the assignment's already been posted, so I guess I can't. But yeah, but if you look into what we talked about in sections 8.2, you should be able to answer this part, okay? What we have here is we have the equation of the regression line. I called this y hat. Sometimes they call it E of y, the estimated value of y. And they want the y-intercept and the slope. The y-intercept is the number over here, and the slope is the other number that's next to the variable x. Okay, and we talked about how to get these. It comes down to using this data here. Okay, the slope is what you have to find first. The slope is the slope. Hold on, let me look. Okay, the slope is determined by the ratio of the standard deviations. Yeah, this data here is weird. Yeah, okay, let's see if we can. Did they give us we need the standard deviations of these, and then we need the means. And I'm not sure if I see the mean here. I thought it might be this word estimate, but that doesn't seem to correspond to. Oh, it says intercept. Are they giving us the intercept right here? I don't know how to do this one. I'm not sure what this. Okay. Yeah, you were right to ask about this question. I'm confused on this one because this isn't how we did it. If we had the standard deviation of the x's and y's, the horizontal, the cans of beer and the VAC, and we had the correlation coefficient, we could compute this, the slope, and then we could use that, and if we had the means of the x's and the y's, we could use that to find the intercept. But that doesn't seem to be given here. So here's what I'm going to do. I'm going to give everyone full points on this problem, so don't worry about it. I'll let you skip this one, okay? The answers are just the two estimates? Okay, so someone's chatting and said that if you just use the two estimates that are given, it accepts that as the answer. I don't know. The word estimate is not very clear. I don't even know what that means. So I apologize. This was given as a recommended homework for this book. So I don't know why it's not as clear as it should be. So anyway, whether it works or not, I'm going to let you skip this. I'll go through and give everyone full points on this one. Sorry about that. Let me look through and see what your other chat messages were about recommended problems here. 4, 5, and 6. Okay, well, hopefully these are better. Okay, oh, this is 8.2, 4, 5, and 6. And number 1 in 8.2. Okay, let's get out of section 8.1. Okay, you know what I'm going to do? Before I go through these problems, I'm going to review what we talked about last time. Okay, I want to finish reviewing that, and I'll touch on some newer material, and then we'll come back here. Okay. So let's go ahead and I remember I had slides for this, right? Let me pull those up. Okay. Just a review of what we talked about last time in section 8.1. This is 8.1 here. We talked about different types of correlations, linear, nonlinear, no correlation at all, what those look like, right? We talked about positive and negative, right? Whether a correlation is positive or negative if it's linear. And we talked about this thing called the correlation coefficient, all right? And I talked about how you would compute it. This is the formula. I'm not going to ask you to use this formula to compute it, but we went through why this makes sense for determining this thing and what it is. What is it? Well, that's described right here. It describes the linear correlation. R will always fall between -1 and 1. If R is near 1, it means the correlation is strong and positive. If R is near -1, it means the correlation is strong and negative. And if R is near 0, it means the correlation is weak. Okay. Or you might, if it's really close to 0, we might think that there's no correlation at all. So we're really looking to see how close it is to +1 or -1. That's good. If we get it close to +1 or -1, that means we have strong correlations. And so that's what we talked about last time. We also went into section 8.2, the last section we'll be covering. And we didn't quite get through all this, so let me finish going through this. We talked about how to find the least squares regression line. That's the line that best approximates the data. And then from that, the equation of that line is what we call the regression model. So we want to interpret that model. And then what we haven't talked about yet is extrapolation. And there's a couple topics we won't be talking about in this section, so keep in mind that we're not covering everything that's in the book. Come on. Okay, here we go. So the least squares line is, you know from algebra that a line has the form y equals mx plus b. Well, here they've written in the form y equals b plus mx, okay? And in place of b, they wrote b0, and in place of m, they wrote a b1. b0, which was the b from algebra class, is the y-intercept. b1, which is m from algebra class, is the slope, okay? When you find these parameters, the first thing you find is the slope. The slope is the ratio of the standard deviation of the y values divided by the standard deviation of the x values. And this should be very familiar to you because you know from algebra that the slope of a line is the change in y over the change in x, or the rise over the run. Well, it's the same idea here. The standard deviation of the y is like the change in the y, and the standard deviation of the x is like the change in x. So this is like change in y over change in x. The only thing is we need to multiply by r to get it to really come out right. Okay, but it's essentially like what you remember from algebra. Once you get b1, the slope, there's a formula that you can use to find b0, provided you have the means of x's and the means of the y's. So you'll be given that. And so you can plug all that stuff in, and then you can get the y-intercept, b0. And now that you have b1 and b0, you have this equation. And this is called the model, the regression model. Okay, and that models the data. provided it is linearly related. It doesn't make sense to do this if the data didn't fall near a line to begin with. Okay, and here was an example where we looked at leucine absorption by oocytes, egg cells, in some animal. I forgot what animal we were looking at. And you can see the data is pretty much in a line. And when you find this line by doing the procedure that we just talked about, you can plot it, and this is what it looks like. That's the line that best fits the data, the least squares regression line. They call it least squares because you're minimizing the square of the distance between the points and the line. So in that way, you're finding the line that's the closest as possible to these points. See, we take the distance between each point and the line, square it, and then try to minimize that amount. And that's why it's called the least squares line. Here's another example. So let's go through this example, and it might clarify the problems on the homework. Finding the least squares line. The rowan, Sorbus acuparia, is a tree that grows in a wide range of altitudes. To study how the tree adapts to its varying habitats, researchers collected twigs with attached buds from 12 trees growing at various altitudes in North Angus, Scotland. The buds were brought back to the laboratory and measurements were made of the respiration rate. The accompanying table shows the altitude of origin of each batch of buds and the respiration rate. Find a linear model which relates altitude to respiration rate. So we have our altitude denoted by X here, the respiration rate denoted by Y here. And we want to find that linear model. Okay. The first thing we should do is verify whether a linear model is appropriate. All right. One thing that tells us that it might be appropriate is that the R down here is relatively large. It's 0.8, can't see it, 0.89. That's pretty big. That's a strong correlation. So that says that a linear model might be appropriate. It's also good to go ahead and take a look at the data. All right. So what you could do is copy this into StatCrunch. All right. So if you put this into StatCrunch, you could load that up and take a look at it. Let me take you to StatCrunch here. And doesn't look like we're there yet. Let me click the link again. No, how do I get the... Oh, it's just pointing me to StatCrunch. It's not taking me to the data. Okay, I'll load it up. Let me unshare and reshare. I just want to make sure you're seeing what I'm seeing. Okay, I think I've got the data saved here. All right. There it is. Here we go. So here's the same data copied into StatCrunch. Okay. And let's just make a plot and just make sure that this is really looking linear. All right. So I'm going to choose altitude as the X, respiration rate as the Y. All right. Well, kind of. I mean, it looks like it might be linear. Right. And you can even have StatCrunch draw the line. A line is a polynomial of order 1. Parabola is polynomial of order 2. But a line is polynomial of order 1. So if you do this, it'll show you the line, right? So this is what we want to find, the equation of this line. Okay. So let's go down to the paper and do this. All right. So what we need is that data that we had. We were told from the data set that we were given the mean of the x's. So we were given x bar. We were given y bar, the mean of all the y's. So they already computed the averages there. We were given the standard deviation of the x's. The sample standard deviation. We were given the standard deviation of the y's. And we were given the correlation coefficient. They called it little r. I'll call it big R because I think big R is what we use in the book. Okay? So there we have it. That's the data that we were given. And if if all you had was the data set, you could compute these values, right? Because you know in StatCrunch how to compute a mean and a standard deviation and stuff. If not, I'll show you how to do it because there's a homework problem like that. Okay. The R will be given to you. Okay. So what do we need to do? We need to find that slope. The slope was called B1, right? So the slope. B1, if you remember, it was like change in y over change in x. So it's sy over sx. And then we know that we have to correct that by multiplying by r. Okay? So there we have that. We can just do that by plugging these numbers in here, right? And then compute it out, right? So I'm going to go and just do that off to the side here in my math software, which needs to load. Give me a second to load that. Here it is. May as well take you over there so not to leave you in the dark. Okay. So yeah, B1 is going to be equal to the standard deviation of y, standard deviation of x was this, and the R was this. So there's our B1. Ooh, small number, ain't it? That's it. So I'm going to write that down on the paper. 0.000. I'm going to go to 4 significant digits. So I could go to 4 decimal places, but I feel like I'm leaving off an awful lot of digits here. Significant digits are the digits that are after the zeros, right? So let's include 4 of those. So I'll put 0.0003185, and that's called 4 significant digits. Okay. The other thing that we need to do. Oh, why is my right mouse button not working now? Okay. The other thing that we need to do is we need to find the y-intercept. And the y-intercept can be found once you find the slope. The y-intercept is let's see, it's y bar minus B1 times X bar. I remember that. I don't even have to look at the formula. The reason I know that is because if you remember from algebra, y equals mx plus b, right? Y-intercept is this, right? So if you remember, what we have is we're calling our slope B1 and our y-intercept B0. So all I'm doing is solving this for B0, right? So if you solve this for B0 by subtracting B1x from both sides, you get this. So this is true for the equation. Now, the regression line always goes through the mean, right? I mean, it makes sense. If that line is going to go through one point, if it's supposed to be modeling the data, it should go through the mean, right? So if I plug in x bar, y bar, this equation should be true. That should be a point on the line. So there you go. That's where this comes from. That's where this equation comes from. It just comes from solving y equals mx plus b for b, right? And plugging in the means for x and y. That's what this is. So these things really aren't as mysterious as they may first seem once you think about them a little bit. Okay, so that's a little thought bubble up here. So that's where this comes from. And we have y bar that was up here, right? So I'll go ahead and just write that in since we can't see it at the top of the page, 0.21. We have B1, that's what we just computed right here. And we have X bar that was given to us, so 433.333. Right, so that's what I've got to go compute, okay? And I did that on my math program there, and I got this. Okay, so we got it. We got B1 and B0, so now we can write down our line, right? As I said, the equation of the line is this, right? So in stats, we usually write it B0 plus B1x, so we write it the other way around, but it doesn't really matter. Y hat equals B0 plus B1x. So this number, x. We put a hat here because y is supposed to represent the data, all right? And this is not data. This is interpolated based on this model. So we wouldn't expect this model to produce actual data values. We expect it to estimate the data values. And so that's why we put a little hat here, okay? And so that's our linear model right there. Okay. Sometimes you'll see it written the other way. I just want to point out that that's totally a possibility, that you could also write it mx plus b, right? So you can put it the other way. What's important, though, is that the correct number is in front of the x, all right? Just make sure when you flip it, you've still got the slope next to the x. The b1 is the number that should be next to the x, no matter which way you write it, okay? So sometimes in the homework, you may see it spelled out this way with the x in the second position. Sometimes you might see it spelled out this way with the x in the first position. Just make sure that the b1 is the number next to the x, and the b0 is the number that's being added to that, okay? So we've done it. Let me share my screen again. Sounds like we got some background music here while we wait. Okay, so interpreting regression model parameter estimates. What do these things mean? Well, you know from algebra that slope represents change in y over change in x. Well, it also represents the amount that y changes if x changes by 1. So if I increase the x by just 1 unit, the slope describes how much I expect the y to change, okay? So that's what it's saying here. B1, the slope, describes the estimated difference in the y variable if the explanatory variable x were to increase by 1 unit. So if we're measuring like distance versus time, the slope is distance divided by time. And change in distance over change in time. That's the speed. So if we're plotting distance versus time, the slope of that curve that we plot is is the speed at which we're traveling. And then we measure that in miles per hour. So the amount of miles we expect to change given one change in time, 1 unit change in time, so per 1 hour. So 60 miles per hour is slope. And if you're filling up a bucket with water, you might be measuring things in gallons per minute or something like this. So slope can measure rates other than just speed. The y-intercept describes the average outcome of y if, that's the y hat, if x equals 0. So that's where the line crosses the y-axis. That makes sense if the linear model is valid all the way to x equals 0, which may not be the case. The linear model is really only valid in the range where we've specified data. Outside of that range, then we get into extrapolations, and those can be very treacherous to do. So in these other examples, the leucine example and the example with the rowan trees, let's interpret the slope and the intercepts. So in this one, I forgot what we computed the slope to be. We did that. Actually, I have the notes from last class. We found the slope to be about 0.03. Okay. What does that mean in the context here? Well, it means that the leucine is increasing by 0.03 nanograms per minute. Leucine increases at 0.03 nanograms per minute. You can see as time increases, the amount of leucine is increasing, and that's the slope is the rate of increase. The y-intercept we got was about negative 0.05. You can see that makes sense, 0.05, so it's about right here. And that's where this line would cross the y-axis. That's telling us how much leucine there was when we started at time 0. That's the initial amount of leucine. Was about negative 0.05 it's estimating. Now, does that make sense? Well, how can the amount of something be negative? So you can see that it doesn't quite make sense. These are approximations. The data doesn't, I mean, our line isn't perfect, right? So we have to keep that in mind. So we have to be a little bit careful. It wouldn't make sense to say we started with negative 0.05 leucine here. In reality, we could expect that we started with 0, right? So the line's not perfect, but it is giving us estimates. In this example, the one we just did, we found a slope of 0.0003. Let's see what units we've got here. We're measuring respiration rate, which is in microliters per hour per milligram. Microliters per hour per milligram. That was the y, and the altitude, and then the x was in meters. So the slope is, the units are microliters per hour per milligram per meter. So it's, when we say that the slope is 0.0003, we're saying that we would expect the respiration rate to increase by 0.0003 per meter. That's how much is going up for every meter of altitude we change. So very, very slowly, it's going up very little. The y-intercept we got was 0.07. So that's saying that we'd expect at around an altitude of 0, maybe the respiration rate might be 0.07. However, we should be cautious about that because 0 is outside of the range of our data, right? This does not include 0 in here. 0 is not between 90 and 790. So really, we should be very cautious about making any statements like that. Okay. And more to that point, that's the idea of extrapolation, extending our data beyond the range at which it was originally defined. And so to point out that an example of this, I just wanted to go to a quote by Stephen Colbert on his, he had a fake news show where he would just make fun of the news. Maybe you've heard of him. And so a lot of the things he said were just satire. And he said in an episode, and this episode was April 6th, 2010. So when those blizzards hit the East Coast this winter, it proved to my satisfaction that global warming was a fraud. That snow was freezing cold, but in an alarming trend, temperatures this spring have risen. Consider this. On February 6th, it was 10 degrees. Today, it hit almost 80. At this rate, by August, it'll be 220 degrees. So clearly, folks, the climate debate rages on. So what did he do? He said in February, it was 10 degrees. Today, it's 80 degrees in April. And then he extrapolated. He said, if we just extend that line into the future, you'd see that in August, it'll be 220 degrees. And you can do the math on this. It's actually correct. Let me just, I think it's worth drawing a quick little picture here. So on April 6th, oh, first he started in February, all right, so February 6th, he said that it was 10 degrees. On April, it was 80 degrees, right? And so what did he do? He said, well, by the time we get to August, he's saying that if we extend this line into the future and we go over here, you'll find that this value is 220 degrees. Maybe we should do the math just to see how it works. What's the slope of this line? Well, the slope of this line is rise over run, right? So what's the change? What's the run? Well, February, March. So there's March, April. That's 2 months. So that's about 60 days, right? So this is about 60 days. And what was the increase? Well, it went from 10 to 80. So that's 70. So the slope of this line, so what Stephen did is he said, well, the slope of this line is 70 degrees in 60 days. So that's the slope. Now, how would we extend this to August? Well, we know the slope is 70 over 60, or 7/6. That's degrees per day, right? So now let's look at how many more days we have from April to August. So let's see, April, May, June, July, August. May, June, July. That's 4 more months. That's 120 more days. So in 120 days, at this rate of increase, how much would we expect the temperature to increase? Well, you take the slope and you multiply it by 120. This is degrees per day multiplied by 120 days, gives you the change in degrees. So 120 divided by 6 is 20, right? And then 20 times 7 is 140. And 140 plus where we ended up, we were at 80 here. So we're going to increase by 140 more. 140 plus 80 is the 220. That's where he got the 220 from. Okay. So we found the slope. He found the slope, and he says, okay, that's the amount that the temperature increases per day. And we know we have 120 days left till August. So that means the temperature will increase by 140 degrees. And so it'll end up being 220 degrees in August. Of course, that's ridiculous, right? The temperature, there's no way the temperature is going to get that high, right? So he's made an extrapolation based on data, and he went outside of the range of the original data, right? And you can see how that makes a ridiculous assertion. There's no way it's going to get that high. And so this is something we have to be very careful about when we use our models. Our models are really only good within the range of the data that we have. Okay, so we shouldn't extrapolate outside unless we have very, very good reason to do so. All right. So you've probably seen these little pictures where like there's these guys in a business meeting and they're like talking about profits and they've got this little chart and the little arrow is just going up because they're trying to convince their boss that everything's fine. And if you just keep, if everything keeps going like it has been, our profits are just going to keep going up. Of course, that's usually baloney, right? They're just doing that to try to convince their boss that things are fine, and they're probably covering up things that are, they probably know things aren't going to keep going up. I mean, maybe they do. Sometimes they do. But anyway, that's why extrapolation and making conclusions outside of the range of data is treacherous. Okay, should be very careful about doing that. So if we go back to that, look at the practice problem down here. Use the linear model relating leucine to time to estimate the leucine level at 35 minutes. Okay, would it be appropriate to use this model to estimate the leucine level 2 hours later? Okay, so let's go down and take a look at this. Oh, where did I put that? All right. This is the question that we were just asked. If you remember from last week, we worked this out. We found the linear model. Oops, that's from this week. That was from today. The linear model relating leucine to time. So X was time, Y was the leucine amount. Right. This was our linear model. Let me copy that down into this area. Okay. And it says, use this model to estimate the leucine level at 35 minutes. Well, remember, X denotes time in minutes. And so if I wanted to estimate at 35 minutes, I'll just plug in 35 for X. And compute that out. All right. So when I do that, I get 0.0, oh, no, not 0.0, 0.9, let me write that again, 0.9765. So what we're saying is we would expect the leucine level to be that. This is the number of nanograms at 35 minutes. Now, does this make sense? Are we extrapolating or are we interpolating? Are we just basing it inside the data? All right, let's go look at the data again. Leucine here, oh, no, here it is. Well, look, the data includes 35, right? See, the data goes from 0 to 60. So what we've done is interpolated what value leucine was right between 30 and 40. This makes sense. It's within the data, right? So this is good. This is a reasonable thing to do. And so what we're doing is we're really just finding, if we go to 35 here and go up to the graph and then over to the y-axis, the 0.9765 is the number we just found. You go from 35 to the graph and then over to the y-axis. That's where we land. And that's what we just computed. Now, the next part of the question is to estimate the leucine level at 2 hours. Would it be appropriate to use this model to do so? Well, 2 hours is 120 minutes. That is not within the range of the data. The data only goes to 60 minutes. So the answer is no. It would not be reasonable. It would not be appropriate to use this model to estimate the leucine level there. We have no reason to believe that the leucine level is going to keep increasing just like this. Just like we have no reason to believe the temperatures are going to keep increasing to 220 degrees in August. We shouldn't rely on this model to be accurate to 2 hours, an hour later into the future. So the answer to that part of the question is no. It would not be appropriate. So for part B, it would not be appropriate to use this model to estimate leucine at 2 hours, because 2 hours is outside of the range of our data. It's outside, and so we shouldn't rely on this. For the same reason we shouldn't expect the temperature in August to be 220 degrees. Okay. Not appropriate. Okay. See what we got here. I think we might be. That might be it. Let's see. Yeah, I got another one, but it's the same kind of problem here. So, yeah, I'll leave that as an exercise for you. So we computed today in class the linear model relating respiration rate to altitude for the Rowan tree, right? So you could use that model to estimate the respiration rate of the Rowan tree at an altitude of 500 meters. If 500 meters is in the range of the data that we had. So you'd have to go check, go look back in this video and then see. Or look at this slide. I think I've uploaded this slide to the course materials, the whole presentation. Would it be appropriate to use this model to estimate the respiration rate at 0? What about 800? So you'll have to check whether these values are within the range of the original data. If they are, then the answer is, well, yes, if the data looked like it was fitting the line well. No, if these, well, if these values are in the range of the data, then the answer is yes, if it's fitting the line well. If they're not within the range of the data, then the answer is no. Okay, and that's it. All right. So that was all of section 8.2, and that's the last stuff that we're covering. Okay. I want to point out, though, that there are some exercises in section 8.2 that require you to use StatCrunch to do some things. So I just want to take you to those exercises and point those out, okay? So let's go over here. 8.2. Here we have a picture of the data and then a summary, and then you can use that summary to make the line. Just like we just did with this last example, with the Rowan tree, and with the example from last week with the leucine. Do it exactly the same way. Shouldn't be a problem if you follow the same steps. Same thing with problem number 2. Okay. Problem number 3. Oh, maybe these you don't. Maybe they're not the ones I thought. Maybe the ones I was thinking of were in section 8.1. Okay, problem number 4. This is the problem. This is what we just did with the leucine. All right, so you're going to. Oh, they already gave you the linear model. Okay, good. So you don't need to do all that. They gave you the linear model. Does it fit the data well? I'll let you answer that. Now they want you to estimate things. Well, that's what we just did with the leucine. We plugged in a number in for X, and we got the estimate for Y. Okay. So all you do here, in this case, instead of an X, they used a T. They said that estimate sales in 2017. All right. So what you have to find out the value of T that corresponds to 2017. Now I'll give you a hint in this problem. It's not 2017. All right, because if the T represents the number of years since 1995. So you need to find the T that corresponds to 2017 and plug that in to the linear model here. And the answer will be the sales. That'll be the answer here. Now, use the linear model to predict the year in which the sales will be 232 billion. Okay, let me take you down to the paper here and show you what you have to do for that one. So they gave you the linear model. They told you that f of t was 9.44 t plus 84.182. You can think of this as y hat equals 9.44 x plus 84.182, right? And what they gave you was, they said to use the model to predict the year in which the sales will be 232 million. So they're telling you what the sales are. They're telling you y hat here. They're saying that y hat is 232. Oops. And they want you to find the year. So they want you to find x. So you need to solve this for x. So that's how we do the second part of that problem. In the first part, we plugged in x and found y. In the second part, you plug in y and find x. Okay, so that'll require a little bit of algebra, but it's not hard algebra. Okay. So that's how that one works. This one's just estimating the profit, so they just want you to find y hat. So that's just plugging in a number for x. And then again, plugging in numbers for x. So these are actually a little bit easier. I did want to show you one problem from section 8.1. I think that was one I was thinking about, where they give you the data and they want you to make a scatter plot. See if I can find that one. Yeah, this one. There's a couple of these. So here, consider the data. And they say, copy and paste this into a statistics software. So here's what we do. We just grab it like this. And I hit Control-C on a PC. I'm not sure what it is on a Mac, but you can also right-click and hit copy. All right. And then you go to StatCrunch. And you, now notice when I grabbed the data, I grabbed the name of the data column too. All right, so it's including the X and the Y. So when I paste it into StatCrunch, I'm going to start up here because I want the X and the Y to appear in the column names. So I hit Control-V, or I think you can you click and hit paste? Maybe you can go to edit and paste. That'll also work, right? Go to paste here. And you can paste it into StatCrunch. And now you can work with this data, right? So you can do a, let me get some things out of my way here. You can do a scatter plot, right, by choosing X and choosing Y. I don't want to hit the compute button, but when you hit the compute, because I would like you to do it. But when you hit the compute button, you'll see you get a nice scatter plot, all right? So that's how we copy data from the homework problems into StatCrunch. Okay. So you might need to do that. And by the way, when you're here, you could actually do those computations, find the mean of X, find the mean of Y, find the standard deviations. I probably should have set some homework problems to ask you to do that because that's useful. I didn't. You go to summary stats and you want to compute summary stats from the columns. And I want to do both columns, so I select both of them. And what statistics do I want? Well, I want the standard deviation and I want the mean. Let's do it in the other order. Mean and standard deviation, right? I hit compute and look, it gives me those things. I can do the mean of the X's and the standard deviations of the X's, the mean of the Y's and the standard deviations of the Y's. The only thing it doesn't give you is the R, right? So if you wanted to do R, it'll be given to you in the problem, okay? So there is a way to get R from StatCrunch, but I'm not going to discuss it here. All right. see what other chat messages we had. Somebody asked about number 4 there. And I think I looked through those numbers 5 and 6. So I think I hope I clarified those things that people asked about. All right. So that's it. That's all we got. So what we'll do is we'll I'll call it for today unless you guys have questions, and we'll just review on Thursday today, this week. And we can talk about anything from chapter 1 through chapter 8. So I'll just be here to answer questions on Thursday. Any questions today?
Not right now.
Not right now.
Any.
Give the homework a chance and then let me know.
I will. I haven't looked at it yet.
Okay. It's not too bad. I think the homework is it's short. I think you saw it. This 8.2 only had 6 questions in it.
Mm-hmm.
All right. All right. I'm going to stop the recording.